I think like 2 days for them to catch up with us in Amsterdam. Mind you, when they showed up in Amsterdam, they had no clothes, because their bags were probably still in some warehouse in Heathrow. So they had no clothes, and by the end of a few days in Amsterdam, we were supposed to move on to Prague for the actual science meeting. We had to do laundry, and the dryer broke, so they stuck their clothes in the oven to warm them off and set their clothes on fire. So, fortunately, they caught this before they had done too much damage, so they were just able to wear them to the airport, which of course, when everybody's worried about terrorism, you want to show up in the airport with scorched clothes. So,
this is the point where you start playing the Benny Hill song.
That's right, it was exactly like that. It was exactly like that. So with all that being said, we finally did get to Prague and get settled into our respective hotels. Oh yeah, we had pictures with the jacket there, there in Amsterdam. And that's Garrett right there, for those of you who know my oldest son. So we get to Prague, and it's a lovely city. It's a great setting for this, international meeting. It's a good place to, of course, go find the landmarks and take pictures with the jacket in front of the landmarks. And it was very neat. And so, meanwhile, my colleague at Caltech had actually gone to LAX security and had somehow recovered my laptop and even printed a new copy of my poster and FedExed it to me. So this is the poster I presented there. One of the problems is, though, is that you always must beware the kindness of your collaborators, because when they actually want to get back at you for something like maybe their license plate holder, they will update your poster for something that they think is important to you. So this is what actually showed up there. And yeah, so you gotta be worried about that. So meanwhile, poster goes up, we're at the meeting, and the first copy of the definition proposal hits the street as far as the big meeting. There's about 2,000 people at this meeting. And the first version of this had come from a blue ribbon panel with planetary scientists and educators and very well qualified people that studied this problem for 2 years. And they came up with this definition, which is a lot of words, which I will boil down to you, and it's very simple: big enough to be a ball. If you take something in outer space and you start lumping material on it, initially it may look like a dog bone or a potato, like we see pictures of asteroids nowadays or comets nowadays. But if you make it big enough, about 1,000 kilometers across, about the size of Texas actually, it'll actually, the gravity, self-gravity, will be enough to pull it into a sphere. And so it'll be a ball, basically. Now, keep in mind that that means that there are now 12 planets in our solar system, at least at that time. So that includes this little guy right between Earth, Mars, and Jupiter, this guy Ceres, which is the biggest of the historic asteroids. But then you also have Pluto and Charon. So they are both planets in this definition. And actually, I think strictly speaking, in this definition, the Earth's moon also gets considered that. So both the Earth-Moon system and Pluto-Charon become a binary planet.
Did they have Vesta at that point?
They knew of Vesta, but so the biggest of the historic asteroids, Ceres, Juno, Pallas, Vesta, of those, only Ceres is big enough to be a ball. And we actually have pictures to prove that now. Vesta's just a little bit out of true. Yeah. So, yeah, so we had Pluto and Charon, and then we had 2003 UB313, better known as Xena at this point. And so, 12 planets, and people start to grumble. And there are interesting things going on. I will point out, as I just mentioned, that you have the question of, do you actually have binary planets? The notion of the barycenter comes into play here, which is with Pluto and Charon over here, the two bodies actually orbit around a common point exterior to both planets because of the relative masses of the two objects. With the Earth and the Moon, you actually have the same sort of thing going on, except that the barycenter is just interior to the Earth. So if you look at it right here, it's much closer to the surface of the Earth than it is to the center of the Earth, because the Moon, while quite a bit smaller than the Earth, is still pretty substantial, so it does yank on the body, and this is why you get tides. But this is also why you get kind of dumbbell sort of motion between the two bodies. So that's just something to keep in your brain and think about. Astronomy, by the way, as an enterprise, is quite comfortable with the notion of binary stars and binary asteroids. They don't rankle at that notion. And so the thought that there could be binary planets should not have been such an anathema to astronomers. But I think a few people had that hard pill to swallow. So we had this definition that was sitting up right here. But an interesting thing happened as the meeting wore on. This IAU meeting, it's actually kind of a death march. It's 2 weeks long, a real slog. I had actually just shown up for the second week, and so an interesting thing happened on the way to the end of the meeting, which is this definition that had been worked up by this distinguished panel for many years' time got tossed out the window, and a new one came into its place, which had the benefit of having a lot more words in it. I guess that's what they were shooting for. And I'm not even going to dwell on that. What I am going to do is, again, try and distill it down for you, which is there are two pieces to it. There is planet, which is big enough to be a ball, which we already started off with. But it also has this extra little clause here, this thing right here. It has to clear its orbital zone, which I have always basically simplified to, it has to be big enough to be a bully. It has to be big enough to push everything else out of its way.
So that's why Ceres doesn't count?
That's right. Because there's other stuff in the asteroid belts. This is why Pluto doesn't count. But part two was the definition of a dwarf planet, where you're still big enough to be a ball, but you're not pushing everything out of its way. So Ceres then is a dwarf planet. Pluto's a dwarf planet. And if you're not even big enough to be a ball, then there's this third category of small solar system bodies. And so that was thrown in there too. So this gets thrown out to us, and there is the vote. It's the very, very important vote. We're sitting there taking selfies, you know, like, woohoo, making history. And it was just really crazy because the resolutions that were presented to the people in the audience at that point, I mean, I'm a chapter advisor for a college fraternity, and I've seen better parliamentary procedure in that venue than in this place. We would be halfway through a vote, and people would be putting motions in to change what we were voting on, and it was getting accepted. And they desperately needed a parliamentarian there, and they just, yeah, it was a mess. So, yes, sir.
How many people voted?
We'll get to that. Yes. Not a lot. So, all this stage being set, I will make a few remarks in the defense of the IAU, the International Astronomical Union, of which I am an officer, by the way. The IAU, the International Astronomical Union, actually does very useful things. And most of them are, as I said, very boring. So these are the other things that were voted on that year. A resolution defining the precession theory and definition of the ecliptic, so basically coordinates on the sky. When you're an astronomer and you say, oh, I looked at this thing and it had this position on the sky, this red ascension, this declination, you have to be using the same system that everybody else is using, otherwise everybody else is going to try and point their telescopes at it and not find it, because you've used a definition system that they don't agree to. So you want to have a single uniform set of definitions in that regard. It's like basically saying, you know, what are the units on your roadmap going to be? How are you going to call it out? Resolution 3, the barycentric dynamical time. So as the Earth spins, that defines the day. And the Earth actually has the unfortunate propensity to sometimes change the length of its day ever so slightly. And so do you basically reset your clocks or not when the Earth skips a second or so every 5 years? This is the sort of thing you vote on. So generally very boring stuff, actually, but actually tremendously useful, particularly in this age of extremely high precision astronomy. So the other thing that has happened over many years has been that planets come and planets go. So if you look at an old textbook here, this one is from 1826, I believe. This was actually a very, very interesting, what's the right word, interregnum where between 1801 and 1807, the 4 biggest asteroids have been discovered, and then nothing. There had been nothing discovered in terms of asteroids for about 40 years. And so for that time period, those bodies were basically considered, well, they're, that's it, and so they must be planets. And also during that time period, the planet Uranus had been discovered, and so it had gone by the name of Herschel, the original discoverer. Neptune hadn't been discovered yet, but when Neptune was originally discovered, it was called George, for one of the kings, I guess. So if you actually look in this book, you can zoom in on the planets themselves. And here's Herschel. You can see Herschel hanging out with its moons. And you can also then look at the inner solar system. So let's see, here's the outer bits. You have Jupiter, Saturn, Uranus. And if you zoom into the middle here, you recognize all this, right? So let me give you a hand with this. Here's the things we know. Earth, Mercury, Venus, Mars. And what's interesting actually is if you look at these orbits, each one of them is labeled with a symbol. And so it's from those symbols that you can actually disentangle what the rest of this is, which is you can pull out the fact that Pallas, Juno, Ceres, and Vesta are these bodies here because they're labeled with their symbols. They actually gave unique character symbols to, I believe it was the first 37 asteroids, at which point they just threw their hands up and quit, which is good because we have about 300,000 asteroids known.
Oh, he says it's beta market.
Yeah. Yeah, now we just have telephone numbers. So that's what the solar system looked like with its planets. These were considered planets up until the mid-19th century. So, but as we learn more, and as they, in 1845, it really got uncorked, and by, I think, like 1850, they had discovered easily like a dozen more asteroids, and they realized that they were in for trouble if they considered them all planets. Again, that's actually kind of a weak argument. Is it the problem if you have too many of something?
Too many, so.
So we'll come back to that point in a second. So at this point, we're going to step back, and we're going to go into the wrong building. So when I was an undergrad, I had this physics professor, Fred Gunsel, and we would ask him certain questions, and every now and then he would come back with the response of, wrong building, we're here in physics, across Ankeny Field is metaphysics over in the philosophy department. So unfortunately, we have to do that. And the warning here is that I have a liberal arts degree from that college, Whitman College. Most of my contemporaries from those days became lawyers, and so this is part of my disclaimer that is running throughout the talk here. But I also, I love this quote from Die Hard, best Christmas film ever, that Hans Gruber is talking about the benefits of a classical education, just before he kills Mr. Takagi, so great film. But what is the purpose of naming? Why do we do this whole thing? Why do we have definitions? And you really want to kind of boil it down to, what are we doing in science? We're trying to discover things, but not only do we just discover things, we actually organize that knowledge too. And part of organization is the taxonomy, the practice of basically classifying things and giving them names. A piece of taxonomy is nomenclature. Inside of astronomy, we also have the practice of giving things very, very nice names, and goes by the name of onomatology. But it's taxonomy and nomenclature that I want to look at in terms of how you categorize things. And there are 3 principal theories of categorization, which is classical categorization. This is the approach that was first really codified by Plato. And you basically take things with similar properties and you organize them together. The other thing you can do, the more modern approach, is conceptual clustering. And this is kind of a meta approach where you basically take the definitions of things or the descriptions of things, and based on the groupings of the descriptions, you glum things together. The other thing we do a lot in astronomy is this last one, prototype theory, where you basically come up with something saying, this is your prototype object, this is your best example of the sort of thing you're looking at, and we'll use that to basically gather to it everything else that looks like it. A funny part about doing this in astronomy is the rule of thumb is that after you've gained enough knowledge, the prototypes are generally non-prototypical. So the best example of that is T Tauri stars. There was a star called T Tauri, which was the prototype young stellar object, the prototype object that is a baby star, basically, that has planets forming around it. And from that, we've generated basically a whole description of what a T Tauri star should look like, what a general young star should look like. And as we've learned more and more about T Tauri itself, it's completely outside those boxes. And as we've discovered more and more things that we thought were T Tauri stars, like these little protoplanetary disks in the Orion Nebula, the proplyds, those are those little lumps in the middle of the picture. Those look more like what we think they should look like when we are now more thinking of the canonical young star object. So the funny part is that this is how astronomy often works, and this is how maybe Pluto ran afoul of the whole notion of planet, because when we had the classical 9 planets, we had the 4 terrestrial planets, we had Earth, we had Mercury, Venus, Mars, then we had the 4 gas giants, Jupiter, Saturn, Uranus, and then we had this other thing that didn't quite fit any other box. And so that confused a lot of people. So circling back to the IU definition, which again, as I've noted, has a lot of words, I will again magically distill it down. There is the big enough to be a ball and big enough to be a bully. A great little graphic I found here showing a round bully. And we will now take this definition and use it. Let's have the pub quiz. So first question is the Earth a planet?
Yes.
No. As the people in Chelyabinsk, Russia will tell you, we have not cleared our orbital zone.
Oh.
There are things that get in our way, and you know, sometimes more catastrophically than others. But if you are appealing to the lawyer in me, we have not cleared our zone.
Gerard,
yes.
Did this object come from our zone, and what is a zone? What's the definition of a zone?
So this is one of the problems of the definition of planet, is that that's not defined. If you talk to a planetary scientist and you ask, well, what does that mean to clear your orbital zone? They'll be like, hell if I know.
It sounds like something you'd say before you excuse yourself to go to the bathroom.
Yeah, that's right. I'm going to avoid my zone. So the next question, is Jupiter a planet under this definition?
Yes.
No. Jupiter has so much gravitational potential
that it populates itself.
It populates basically the gravitation. So if you draw a triangle between the Sun and Jupiter and about a 60-degree equatorial triangle, you get to these Lagrange points. These are basically gravity wells that are defined by the vast gravity of both of Jupiter and the Sun. And it tends to collect objects. And in fact, they've named these objects the Trojan asteroids. And they've even gone so far, they've actually done a really good job of the nomenclature here. They've even gone so far as to separate them into the 2 camps, the Greeks and the Trojans, as part of the Trojan War. And so these are objects that are in the path of Jupiter. They have basically a 1 Jupiter orbit radius that they go around. And so with that, they are in fact sitting in Jupiter's orbital path, which Jupiter will never clear out because in fact it's preferentially situated to keep them there. The next question is Mars a planet?
Yes.
No.
Yeah.
So it has Phobos and Deimos, which are probably captured asteroids, which until they crash into Mars, which they will, are not cleared out of the zone yet. Mars also, in fact, has Trojan asteroids. It has at its kind of gravity wells with the Mars-Sun system. It's been found that there's a small number of asteroids discovered that sit in those wells. So in L5, I think it's the leading edge. I think it's the trailing edge one. There's a number of bodies, and there's even the one found at L4. So this immediately comes to mind with the question of, which planets, where are all these Trojans? So there's a bunch of Trojans out there. And so in fact, Venus has a Trojan asteroid, the Earth has one. You'll notice from these telephone number designations, the year of the discovery. And so all this is actually pretty recent. We're getting better and better at finding smaller and smaller stuff in our solar system. In fact, the only things that don't have at least known Trojans is Mercury and Saturn. Mercury, because it's too close to the Sun, the Sun's tidal forces, I think, disrupt everything. Saturn, because of the influence of the gas giants, both interior and exterior to its orbit, so both Jupiter and Uranus
So
are...
Saturn's not actually clearing its own zone, it's just having its own cleared
That's right.
elsewhere.
So Saturn and Mercury, Saturn in particular, is a planet by virtue of the fact that there are other large bodies that don't themselves qualify to be
Wait, I
planets.
thought it had to clear its own orbit.
Ah, that's a good point, actually. So, yeah, I should come back to that and, see, peer deep into my interior lawyer again. So this then sets the stage for me to maybe make a few comments on the current IU definition, of which I have, I think, 8 at this point. So there were problems with this definition, one of which, as you were asking about, is representation. In the IAU, there's about 10,000 members worldwide, and there were only about 2,000 at the meeting in Prague, of which most had left by the time that the final closing ceremonies where the vote was taken, because it's such a long slog. It's a 2-week-long meeting. You don't want to stick around. And so there was only about 400 of us in the room at the end, and doing the various votes on this resolution. And the votes themselves didn't have representation from the people that actually knew what the heck they were talking about, which is the planetary scientists, the people that actually publish in Icarus rather than the Astrophysical Journal, and are talking, not about stars and galaxies and that kind of thing, but actually publish papers about volcanology and Enceladus and the rings of Saturn and this kind of thing. People actually study the bodies in our solar system. So there was very little representation from them. As one of them has remarked to me, one of my colleagues up at Lowell, what if we had our own meeting and came up with a definition for the word star? Because there is none. There's no official definition for the word star. And we would come up with a new name for it, giant bag of gas or something. And that this was something that was not done very well. So the other thing that is interesting is there was a very bad process going on. It was a bit of a circus, actually. And they've foolishly left a video of the entire proceedings online. You can go out and find it, and you can kind of see how it just kind of meanders in its organization. And yeah, so it was a bit of a circus. There's a great little graphic showing the only thing that you can get out of a circus. The other thing that is a problem is that the definition very clearly limits itself to the solar system. It says this definition of planet is for the solar system. And so that means there are 8 planets in the universe, which the Kepler spacecraft, which I sat on that review board for, flew after the 2006 meeting. It went up into space in, I think it was 2009. And since that time, Kepler has found many thousands of planetary candidates. And in fact, I think over decisions here at home. So this is very important. The thing that this definition also completely missed was the other end of the question, which is not how small can something be and still be a planet, but how big can something be and still be a planet. Because we have stars, like our sun up here in the corner. We even have small stars that are redder because they're cooler, they're giving off less energy than the sun. And then we have things called brown dwarfs. And these are things that early in their life, their gravitational contraction heats up the core, and it makes the core hot, but not so hot that you're going to sustain regular nuclear fusion like a star has. But it is hot enough that you can do a little bit of nuclear fusion. You can take the deuterium that happens to be contaminating the star and fuse all that and make it shine for a short period of time. But once the deuterium is gone, it's over. And they stop generating their own energy. So they're kind of a star at the beginning of their life, but then they're kind of a planet at the end of their life. So they're actually in this no man's land in the middle. Defining that range is very interesting because we have a pretty good idea on how to define it. Between about 13 Jupiter masses and about 80 Jupiter masses is the range where you get that very limited lifetime of deuterium fusion. Heavier than that, you actually are able to sustain regular hydrogen fusion and be a regular star like Gliese 229a here. South of 19 Jupiter masses, or sorry, 13 Jupiter masses, you get things like Jupiter where you don't even get deuterium fusion. So that's a very interesting thing to define because we're finding a lot of brown dwarfs in our immediate solar stellar neighborhood right now. Yeah, there's very bad specificity with this, as already discussed. You know, there is no scientific rigor in the statement. Cleared the neighborhood around its orbit is the language. It's very subjective. It does not account for the fact that we have things like Meteor Crater here in Arizona, and it needs a little bit of work on that. The other thing that's very odd is a dwarf planet in this definition is not a type of planet. It's an entirely separate thing. It's a not unbreaking space between the words dwarf and planet. It's also very PC. Elsewhere in astronomy, you have dwarf stars, you have dwarf galaxies, and they're a kind of star and they're a kind of galaxy. They're actually variations on the theme. They're still considered full-fledged stars, and they're still considered full-fledged galaxies, but they just happen to be of a class that's the dwarf star, dwarf galaxy. That's not the case here. The dwarf planet is not a planet, and it's very confusing. And I think finally, the main criticism I would have would be it's very based on context, as far as if you were to take the Earth, same thing, and move it to the Kuiper Belt, it would no longer be a planet because it wouldn't have cleared its zone. It wouldn't have the time to it. The orbit would be longer at that point. It simply doesn't pass the Star Trek test, which is, you look out the window and say, oh, it's a planet. It assumes that you have perfect knowledge of not just what you're looking at, but the entire environment as well. You know, it's like me being able to say, you know, I know that this is a couch because I know there's a bed in the bedroom upstairs, which I don't know that. You know, there are occasions when you don't have time to survey the entire solar system you're in. You're in a bit of a hurry, so you need to be able to know if something's a planet beneath you or not, just by looking out the window. So, what would be better than this definition? And what would be better would be to just make it simpler. Just say, is it big enough to be a ball? And that does include things like Ceres here, rotating away, which it's very interesting little shiny bits on there. We're still trying to figure out what that is. And then, so that defines the low end. And then not a fusion reactor of any sort, and that makes it possible to define the high end. Those are the two pieces to the equation. And that brings together that concept into a box, a scientific box, that then gives you something that has common interest. You actually are starting to talk about bodies of a whole range of sorts that have many common physical processes, and it's a scientifically useful handle on the notion. So this is actually changing that into science language. So big enough to be a ball is basically sufficient material to be in hydrostatic equilibrium, and then not generating energy through thermonuclear fusion. That's the taking that and actually dressing it up in the right scientific language. The implications of that is that we have many, many planets in our solar system. You can still say, okay, we'll have this whole clearing your gravitational zone thing. You can actually make a language a little better and say it's the gravitationally dominant body in its orbit. And then you have a concept of major planets again. That would leave us with 5 or so minor planets, including Pluto, including Ceres, including Xena, and with many more on the way, because there's actually quite a few candidate objects that have already been discovered, and it's just, their size is uncertain, because again, it's this question of how do you actually determine a size when all you see is a speck of light in the sky, like this guy right here. And this accommodates all kinds of other things, like what happens to a planet that gets thrown out of the solar system? This is thought to happen. You have these rogue planets that are wandering the spaces between the stars. That's a concept that actually is accommodated by a new definition like this. You have the Tatooine planets, so planets that go around 2 stars at once. That's still a planet. And then you also have the binary planets, the Earth-Moon objects, the Pluto-Charon object. That's all fine here. Here's what some of them look like, the recent discoveries. We have Eris, which was formerly known as Xena. We have Pluto, which has all these moons that have been discovered around it now, in addition to Charon. There's Styx, Nix, Erebus, Hydra. Makemake, Haumea, Sedna, Quar, even things like 2007 OR10, so new that they don't even have names really yet. And so these are all things that are in the category of basically being very small, but still planetary-like objects, planetary mass objects. Some of them are very interesting, well, they're all very interesting, but for example, Haumea you'll notice has a very odd shape. It's spinning really fast. So it's still in hydrostatic equilibrium. It's just that the centrifugal acceleration is trying to pull it out of shape. And that's what hydrostatic equilibrium looks like for a rapid rotator. I haven't filled out this slide yet. I'm still trying to figure out what I can tell people they can do about this. There are people that still, every anniversary of the vote, have protests like this one in Seattle. I should know that from street corner really well. And I think it's Greenwood and 85th Street. But yeah, I want to leave people, this is one of the things I'm trying to put into the talk yet, is telling people what they can do. Part of it is letting people know that as long as they continue to agitate about how this is silly, at least the existing definition from the IAU, that things will eventually be right. The scientific process will do the correct thing. So Xena became Eris, as was noted before. Xena does have its little buddy that had been going by the name of Gabrielle, and now is known as Dysnomia. Fortunately, there was a little reference slipped in there by Mike Brown, who proposed these official names in the end. It's much more classical names. Dysnomia is the goddess of lawlessness, which maybe is a little nod to our friend. And then the jacket. What happened to the jacket that started off this whole tale? Well, we gave it back to our friend Mike. And one of the things was that every place we took the jacket, we bought a pin. And we didn't want to stick all these pins in his jacket, which he's wearing in this picture. So we gave him another jacket, which we put all the pins in. We did keep a little piece of his original jacket. See, this being one of these undercover cop things, you could actually get different labels that zippered in. So we unzipped the original police sign, kept it, ordered a replacement one, and so fixed that. But we had one more place we wanted to go with the jacket. And so we took that little bit of extra jacket, and we actually managed to get it a ride. And every night now it orbits overhead in the Genesis 2 prototype space station. So right here is the exterior view of Genesis 2. It has an interior camera, so you can see little bits floating around. And from my front doorstep, I took this image of Genesis 2 going by a few nights ago. And so we were able to get the jacket to the last place that really needed to go. And never turn your back on astronomers, I guess is the main lesson here. So with that, I will take questions.
I have a question.
Yes, sir.
When you left your poster and your laptop behind, speaking of turning your back on astronomers, did you check and make sure that everything that you left behind came back to you on all the whole pieces, or is there some part of is there a chunk of memory that's going to be flying up into space?
So the poster showed up in its modified form in Prague, but the laptop itself was fine when I got it back. So there was no Trojan horse installed or anything like that. Yes?
Did you get your job at Lowell because you voted for Pluto?
It certainly didn't hurt. I certainly pointed that out, actually, when I was interviewing. Yeah.
And then what was actually the vote of the 400?
So this is another problem, is that on the original vote on Resolution 5A, they did actually not take a tally. So that was in part because...
You guys are scientists, right?
Good point. So there were subsequent motions which had, each subsequent motion went from like 300 to 100 to like 250 to 150, and there were some in the end that failed. So one of the motions was a motion to define the first big 8 planets, the terrestrial planets and then the gas giants, as the classical planets, and to make that official definition as well, and that failed. Yeah, the whole thing was not run very well. And bless their heart, the people that do this kind of thing have no experience with parliamentary procedure, but it really was necessary.
Did they learn anything from it?
They learned not to ever entertain a new proposal to redefine planet. They consistently refused to revisit the question.
Can you speak a little bit more to the functional change that would occur if it was technically called a planet in the astronomy community? What would be the difference?
So I would say, I would answer that in two ways, one of which is A, nothing, because these worlds are interesting in their own right. Pluto is very interesting from the sense that rather than being the oddball, it's now being realized that it's the progenitor, it's the prototype, speaking of classification theory again, it's the prototype of a whole family of bodies that are a lot like it, and that they are very interesting and a very significant component of our greater solar system. That being said, if you go to Congress and you're shopping around for $750 million to fly a spacecraft, it's a lot sexier to say you're going to a planet than going to a dwarf planet or an asteroid or a comet or this kind of thing. And so there are political implications of that. And so when Alan Stern visited and gave his talk on the New Horizons mission, he gave many, many very compelling scientific reasons to visit this object, and that's what carried over the National Academy of Sciences in endorsing the mission in 2000 that got New Horizons built and funded. But I'm sure there was no small piece of it that when NASA went to Congress and said, you know, we need $700 million to build this thing and go, that you know, the notion of completing the first reconnaissance of the planets of the solar system with an American spacecraft, I think that was not lost on them. And you know, it's a bit jingoistic, but you know, the fact that all of the major planets in the solar system have principally been visited first by American spacecraft is a big deal.
That whole planning thing reminds me of, you remember when the whole like neutrinos might be faster than light thing came out?
Which that?
When people were saying neutrinos might be faster than light, and
yes.
they found it at CERN. And that was when I was studying physics, and this came out, and we all went to talk to our professors, and we were like, you do realize that the grants are coming out in about a month. Like that, and they were saying like that's basically why they just pushed that paper out there, and then later went back and said, oh, it was an instrument calculation failure, but they wanted to have something exciting when the money was coming around.
What's interesting about that particular discovery was they did it pretty well in the sense that they had a very, very sensational discovery, but it also was one that didn't make sense. And they put it out there in a way of basically asking the question of, well, we have this result,
Yeah,
we think it should be wrong, we don't know how it's wrong,
Yeah,
and so
they-
they invited the criticism.
Yeah, they put it out asking people to look for
Yes.
mistakes. So, yeah, they did that very well. And then, of course, some of the media outlets took it as that, oh, is Einstein wrong about everything?
That's right.
And,
Yeah, and that actually maybe stands in contrast to the Bicep 2 result, which was this result that came out of Antarctica where they thought they had seen the fingerprints of the Big Bang turning up in the cosmic microwave background, that it basically had been gravity waves.
Is that the thing where they have like that big whole like tank under the ice?
No, no, it's something else.
Okay.
That's Ice Cube.
Yeah.
But Bicep 2, yeah, they had this result and they put it out there, and it, in the end, they had kind of skimped on one piece of the reduction where they had knowingly skimped on how they had done that. And when that piece of the puzzle got painted in with greater clarity, the whole result kind of fell apart. And that was a case where science wasn't done so well, where it was done more by press release than by peer review. So, more questions?
It seems like for our own solar system, there's few enough planets that like to have a category of you know, 4 or 8 or whatever that's full of exceptions, and or you know, like you said, each planet's interesting. Just, you know, it's right. Or maybe if we ever got out to other planets or got much better somehow or other, it might be useful to have you know, just a more set category like the one you need. They're big enough to be round and, or, you know, a ball and small enough to not be. But then I was also thinking like maybe that, because like a gas giant is practically having kind of different critter than a rocky planet, so why not have another categorical line there? But then how big does a planet have to be before it's considered a gas giant? Because I mean, we have a gaseous atmosphere. How thick does the atmosphere have to be before we call it? But then here in our solar system, there's pretty clear, you know, pretty clear difference between Earth and Venus having an atmosphere.
So just like we have with the taxonomy of plants, you know, something can be a tree, but then you can have a leafy tree and a coniferous tree. I think with planets, you could have much the same thing where you have planets, but then you have the rocky planets, you have the gaseous planets, and you also have the dwarfs. And even within the dwarfs, you have the ice dwarfs, like Pluto and its ilk, and even the dirt dwarfs, like Ceres. That's all fine.
Well, why can't you decide, how do they decide they're a dwarf aside from not having cleared their orbitals so much?
So that would be the break point, and that's, again, has its drawbacks in using that as a defining factor. But one of the benefits that we actually do have now in 2015, which we didn't have in 2006, is we now have, you know, a few thousand planetary candidate objects from the Kepler spacecraft, and these are beginning to be studied, and we're being able to not just, you know, in the barest, most tenuous way detect them, we're actually being able to find out more about them. And one of the things that is going on right now is trying to establish the masses and the radii and the densities of these things. And they do appear to be separating into kind of two distinct phyla, the right word, where you have the gaseous objects that have, you know, densities that are much closer to water, basically, and you have the rocky things, which are much closer in density to these things like Earth and Mars. You know, a density of, say, 1 gram per centimeter versus about 3 grams per centimeter. There seems to be actually a pretty clear separation there, and that lets us categorize these things into gaseous versus rocky. And so it's a much more informed picture we have now of this whole series of objects that you can find around stars. And it's a very exciting time, actually, to be in a time where comparative planetology is being done on a grand scale, not just between, you know, things you can number on your fingers.
You mentioned gas giants and ice dwarfs. Do we have any ice giants?
So within the gas giants, there is Jupiter and Saturn, and quite often Neptune and Uranus get called ice giants because they actually are quite a bit more dense than Jupiter and Saturn. They have quite a bit more ices in them. They behave apparently a little bit different with how their weather works. So that is again a category where we have a bit more information now to maybe set up a special box for that.
It's interesting to think about what the publicity for this debate would have been if Pluto was simply called a small planet. If it hadn't been, if the word dwarf had not been used. Probably.
Well, and this is one of the things where astronomy is hidebound by its history. Astronomy is a fun science because it has such a rich, lengthy tapestry of history behind it. But it often will get tripped up by that. So in the sense that the main center for tracking asteroids back in the East Coast is called the Minor Planet Center. And based on just that historical fact, it was decided we couldn't use the word minor planet to call out a separate class of planets such as Pluto. And this was one of the debates that went on in Prague, was, you know, can we call it that? No. Can we call it a Plutino? No, this gets confused with the geology term. Can we call it a Plutoid? No, it's because it's used over here. And it was all trying to be decided on the fly in that meeting, where people are making these proposals and motions and trying to get things into the voting process, you know, right there, and it was just a mess. It's a crazy mess. All right. Thank you very much.